Hello, hello.
So I'm going to see if I can download it on one of the computers.
Hello, hello. Hello. Hello, hello.
I agree. I open
Okay, so this is the lecture summary for today. And there were some excellent questions that I'd like to address later, particularly the transformation from generalized eigenvalue problem to standard eigenvalue problem. And I'd like to continue to push forward. See, yeah, so this is what we did last time, particularly the practice, exam practice problem, okay, that I listed at the bottom here, together with other work that we did. And so we'll go to orthogonality of eigenvectors. This is beginning of week 6. And this is not new because you have encountered orthogonality of the eigenvectors back in meeting 13. Let me bring up the mask here. Yeah, before I forget, you can check the list of the active learning credits for meeting 16 and meeting 17. I have already put on this daily lecture summary, and there's a signature sheet there that is over here. And so I showed the slides. Okay, yeah, the handwritten notes, my handwritten notes from last time. I can pull it down. Actually, yeah, meeting 17 was from last time. Probably a move behind here. Okay, so let's look at, let's review quickly meeting 13. So here is just to go up so that you can review. You know, I use a simple system of springs in series, and just for statics, arrive at the standard eigenvalue problem. You know, basically to motivate the different properties of the stiffness matrix here, and explain diagonalization. And towards the end, you would see that I have explained, you know, once we found these two eigenvectors for the stiffness matrix, then you see that you notice that the two eigenvectors are orthogonal, right? Take the dot product of these two vectors, right? 1 times 1 plus 1 times minus 1, that's 0. These two vectors are orthogonal to each other. And in meeting 14, right, the length, the magnitude of these two vectors are not unit, so you normalize. Okay, so the length is 1 over square root of 2. So normalization means to make the vector to have a unique length. Okay, so these are the concepts that you would use for the generalized eigenvalue problem, and we'll continue with section 53D. All right. Now, section 53D, I have, this is the table contents. Let me bring So here's section 53D, and let me scroll down so you see where we are at. Okay, so we have gone through this. This is to find the second eigenpair. That's what we already did. Okay, and so now we are here. We will talk about the mass orthogonality of the eigenvectors. And so this is a generalization of the concepts of orthogonality. So let me use this screen here so I can zoom in. Okay, so this is mass orthogonality. Okay, so what does it mean? What it means is that the two eigenvectors of the generalized eigenvalue problem are still orthogonal to each other, but now with respect to the mass matrix. And you know, the dot product is now generalized to contain the mass matrix. Okay, so phi1 transpose m times phi2. Now, in the case of the standard eigenvalue problem, the mass matrix was identity, so you get back to the regular dot product, right? Phi1 transpose times phi2. So that's what we did before. So now you just squeeze the mass matrix in between. Phi1 transpose is the row matrix, because phi1 is a column matrix, right? The transpose, it becomes the row. So that's the row with the first coefficient being 1, second coefficient is square root of 6. The mass matrix is a diagonal matrix with m1 equal to 2 and m2 equal to 1/2. Now, this column matrix here is phi2, and phi2 we have found that it's 1 and minus 4 over square root of 6. Okay, so if you compute out, multiply out, so take the mass matrix. So what I did here is I took the mass matrix. Let me write here for you. I took the mass matrix times phi2, and this product here gave me this column matrix, right? So 2 times 1, 2, and 1/2 times minus 4 over square root of 6. That's minus 2 over square root of 6. Now then you can take that row matrix, that's phi1 transpose, multiply by this column matrix, you get a scalar, a number, that is. And that number turns out to be 0. So therefore you say that the eigenvector phi1 is orthogonal to the eigenvector phi2 with respect to the mass matrix. Okay? So that's orthogonality for the case of generalized eigenvalue problem. And let's review quickly once more. You see the orthogonality in the case of standard eigenvalue problem. You can think of phi1 dot with phi2 is the same as phi1 transpose times phi2, right? Let me write in my notes so that you have something to refer to. What I was saying is that you can write phi1 dot with phi2 as phi1 transpose times phi2. Okay, it's the same thing. All right, you get a scalar quantity. So a generalized, and this is the same as writing with the identity matrix in between. Okay, so I can write like this. I think of this as having an identity matrix in between the two eigenvectors, so that the result is still phi2, right? So now this is for the standard eigenvalue problem. For the generalized eigenvalue problem, let me note down that this is for the standard eigenvalue problem. Okay. Whereas for the generalized eigenvalue problem, you say that you replace the identity by the mass matrix. Replace the identity matrix by the mass matrix. So therefore, the orthogonality. Yeah, I need to. Let me do this. Let me remind you that orthogonality is that the dot product is equal to 0. Right? And now for the standard, for the generalized eigenvalue problem, we have the mass matrix in between. Okay. And so orthogonality means that phi1 transpose times the mass matrix times phi2 equal to 0. All right. So that's what was in my lecture notes, section 53B. And this is a computation. So it's very concrete. Work out, you get 0. All right. In other words, if after you did the problem and you verify orthogonality, and if you did not get 0, that means that there was something wrong in your computation, right, of the eigenvectors. Okay, so that's a check. That's a good check there. All right. Yeah. So here I set the above operation between the eigenvector phi1 and phi2 is a generalized dot product, right? Instead of having the identity matrix in between the two eigenvectors, now you have the mass matrix. So the dot product had been generalized, just like the standard eigenvalue problem had been generalized to the generalized eigenvalue problem with the non-identity mass matrix. Okay, so same thing. And so the generalized dot product between these two eigenvectors, when the mass matrix is an identity, that's the standard dot product. Okay, so you generalize the dot product to the case where the mass matrix is not identity. All right, so we are done with this part. So now comes the next concept, a new concept. Is the modal mass. Okay, there are two vibration modes. There are two modal mass. Now you can think of the modal mass concept let me give a hint. If you look at the modal mass, suppose that you replace M by an identity matrix, right? Then you would have phi1 transpose times phi1. What do you interpret? How do you interpret phi1 transpose times phi1 in the classical vector algebra that you learn? What is phi1 times phi1 transpose times phi1, assuming that the mass matrix was an identity matrix, right? In the case of the mass matrix was an identity matrix, what is? Someone was saying something. Yeah, Kevin.
It's 0, isn't it?
Be careful. This is phi1 transpose times phi1. Phi1 transpose times phi2 is 0. Yes.
Oh, okay.
But here we are talking about phi1. Let me write something so you have in your notes. So recall for the standard eigenvalue problem, what was, let me do like this. Right, the mass matrix is the identity matrix. And let me zoom out so you have the big picture. Right, and this is the same as saying phi1 sorry, I meant to write 1 here. Or you can also say that this is the same as phi1 dot phi1, right? That's what we just said. So what is phi1 dot phi1? How do you interpret phi1 dot phi1? This is regular vector algebra here, right? This should be well known. Someone active learning credit. This is the square of the length, right? This is the square of the length of phi1. Okay, the square of the magnitude of phi1. So you write something like this. This is the technical mathematical notation here. That's phi1, and the double bar here means the magnitude of phi1. And let me move down here so I have some space. And square. Okay, the square of the length. That's the square of the length of phi1. Okay, is phi1 not phi1? Example. Remember for the standard eigenvalue problem, we found phi1 is a column matrix with number with the coefficient 1, 1. So therefore, the magnitude of phi1 square, which is phi1 dot with phi1, is equal to 2, right? And the length is equal to square root of 2. That's why when you normalize, you divide by the length, that becomes because this is from meeting 14, that the normalized, that's phi1 bar, that's 1 over square root of 2 times phi1. Okay, this is called the normalized eigenvector for the standard eigenvalue problem. So similarly, when the mass matrix is not an identity, then you can interpret phi1 transpose times the mass matrix times phi1 as the square of the length, okay, generalized length. And that generalized length is the modal mass, okay? And this is getting into dynamics now. That's why the name modal mass, because it will be the mass for the modal equation once you decouple the two equation of motion. Okay, so the modal mass m1 bar is defined as phi1 transpose times the mass matrix times phi1, and this is the computation where phi1 transpose is the row matrix. You see, phi1 is here. Phi1 is a column matrix. 1 square root of 6. So the transpose the column becomes the row, right? 1 square root of 6. And this is the mass matrix, 2, 0, 0, 1 half. And so if you take the mass matrix times Phi1, you get this column matrix here, right? 2 times 1, 2, and then 1 half times square root of 6, square root of 6 over 2. And then take this row matrix times this column matrix, then you get a scalar, and that's 5. Okay, so this is called the modal mass M1 bar. Let me zoom out so you have the big picture. And so now normalization. So once you have the modal mass matrix, very similar to the case of standard eigenvalue problem, you divide by the square root of M1 bar. Okay? Think of the modal mass as the square of the generalized length. So you take the eigenvector, divide by the square root of the square of the generalized length. Okay? Just like in the case of standard eigenvalue problem. So therefore 1 over square root of 5 times the column matrix of the coefficients of Phi1. Okay, the first eigenvector. All right, so then you do the same thing, exactly the same thing for the second eigenvector to obtain the normalized eigenvector. Okay, and so let me quickly review. Right, first you find the modal mass for mode 2. So that is simply Phi2 transpose times the mass matrix times the Phi2, the second eigenvector. And so the computation is just put in the numbers, the coefficients for the Phi2, that's the column matrix, 1 minus 4 over square root of 6. The transpose is a row matrix, 1 minus 4 over square root of 6. The mass matrix, which is a diagonal matrix, 2, 1 half, and then multiply out, you get 10 over 3. So 10 over 3 is the square of the generalized length. And that's called the modal mass M2 bar. Okay? And when you normalize the second eigenvector, you take the second eigenvector and divide by the square of the generalized length. So divide by square root of 10 over 3, that's square root of 3 over 10. Okay? Whereas this column matrix here, 1 minus 4 over square root of 6 is the same as the second eigenvector. These are the coefficients of the second eigenvector that we found before. So this is entirely parallel to the standard eigenvalue problem. Okay, what we did here for the generalized eigenvalue problem is completely parallel. It's a generalization of what you saw in the standard eigenvalue problem, except that the identity matrix now is a mass matrix, N, which is not identity in general. All right, let's zoom now. Yeah, so this is a remark related to vibration. What I put a note down here is that in general, mode 1 has lower frequency, meaning lower eigenvalue, right? Remember beta 1 was equal to 4 and beta 2 was equal to 9. So 4 is less than 9. So mode 1 has lower frequency, vibrational frequency, and thus longer period, right? Because frequency is inversely proportional to period. So if you have a smaller frequency, then the period would be larger. And also in general, it has a larger amplitude of vibration than in mode 2. Okay, so, and here is the animation. I have some animation that I have prepared. What you want to notice here is that, okay, So here, let me point out the black dot represents the initial position. The blue dot is the mass M1, and the green dot is the mass M2 that is moving, okay, vibrating. In mode 1, you see that the undulation, the oscillation of mass 1 and mass M2 are in phase, whereas the oscillation in mode 2 of mass M1 and mass M2, so in mode 2, I represented the motion of mass M1 by the red curve and the motion of mass M2 by the purple curve. And you see they are out of phase. Okay, the phase angle is actually 90 degrees. They are out of phase. So let's look at the animation. So I have the animation here. So let's bring up. This is Desmos. And yes, so let me put on the projector mode so that it's a thicker line style. Okay, and let me for now close this. And if you look at the result, you see, so mass M1 and mass M2 moves together like this, in phase. Okay. And so this is the code. You see that I can write with Greek letters omega phi, and in the portal of the course, I have a manual showing you how to write these formulas. Okay, let me see. Let me show you. Okay, the portal you can get from Sakai, and I also have it at the top of this. Maybe I don't want to. Let me open another. I probably don't need the meeting 13 and meeting 14, so let me close that down. Yeah, so let's see, the portal is also at the top here. So if you go to the portal of the course, this is where you would find the manual for Desmos. Right here. This is a link. You can read that link to recreate the plots and the animation that I have there. Okay. Yeah, so if you look through the code, it's relatively simple, right? What I did is I defined phi11, which is the first coefficient of phi1. That's 1 over square root of 5. Remember, this is the normalized. This is the normalized eigenvector, but there's some particularities with Desmos is that it doesn't accept the overbar, so I cannot write the bar on top of phi1 to designate that this is normalized. So think that this is normalized. Okay, so phi12 is the second coefficient equal to square root of 6 over square root of 5. That's what we just found at the beginning of this lecture. And for the circular frequency, omega 1 is equal to 2. Remember, beta 1 was 4, and omega 1 is square root of beta 1. So omega 1 is equal to 2. Okay. And how do you animate like this? Well, basically, you just multiply phi1 by sine of omega 1 x. Okay, both coefficients. So what I plot here in blue, is the time. Think of x as time. Okay, x is independent variable, and that you can think as time. So the plot of this function phi11 sine of omega 1x is the blue curve here. That's the sine curve, and up there is the animation. And I'll show you the animation. The green curve is phi12 times sine of omega x. Okay, so how do you do the animation? You do the animation by simply, so here is what I did. I I created a parameter t for time. It can varies. It has a range right now from 0 to 20, but you can increase to whatever number. And then I put the mass m1 at this coordinate. Okay, you see the black dots are the initial position of the mass m1 and mass m2. So basically, I put the mass m1 at minus 1.5, x equal to minus 1.5, and y equal to 2. The y coordinate equal to 2 there. And the initial position for mass m2 is plus 1.5, and then for x and y equal to 2, right? So x equal to 1.5 and y equal to 2. And then to animate, make it move, I see, so the blue dot, which is the animated mass m1, is simply, I set, this is the minus 1.5, so the x coordinate is minus 1.5 tag plus d11, and with the t as a variable, so that allows, when t varies, you see the position of the blue dot varies, okay, and it varies with around the value of x equal to minus 1.5. So as you see, it's completely symmetric about the black dot representing the initial position of mass m1, and I did the same for mass m2. Okay, that's it. That's for mode 1, and I did similarly for mode 2, and I have this link here that immediately bring you to mode 2. Instead of messing with my code, I already saved the this animation for mode 2, and let's remove the code for now. And to observe, you see that, as I mentioned before, the red curve, which correspond to mass m1, and the purple curve correspond to mass m2, move out of phase, meaning that it goes like this. Okay, if it goes like this, that means in phase, and moving like this is out of phase. Okay, so that's what you see there. The animation and the code. You can look at my code. I've already explained the case of mode 1, and this is mode 2, and just 1 point, omega 2 is equal to 3 because beta 2 was equal to 9, right? Square root of 9 is 3. Okay, so that's the animation. And now I have also a link that shows to you both the animation of both cases, putting one on top of the other, so that, oops, this I should not. Sometimes when the computer is out of memory, it gives me that warning. So here you can see mode 1 is on top. Okay, the 2 dots are moving in phase, and mode 2 is below, where the 2 dots are moving out of phase. Okay, and then these are the curves plotted on top of each other, the 4 different sine curves. Yeah, so that's that's the tool thing there. Let me see, maybe. Out of phase is 180 degrees. in terms of the phase angle. Okay. And you can see that from looking at the sign, right? This has a minus sign, and if you compare these two functions here, they differ by a minus sign. Okay, so let me write in my note, so you have something. Okay, so let me write down here. Let me use the same notation. D21 and D22. Okay, so D21 is equal to phi 21 sine of omega 2 t, and D22 equal to phi 22 sine of omega 2t. The only thing that you want to keep in mind, regardless of the numbers, is that you see phi 21 is square root of 3/10. That's a positive number, whereas phi 22 is a negative number. Whatever that number is, not so important, but the sign is important. So let me put in my note here. Okay, with phi 21 a positive number and phi 22 a negative number, right? And so with a negative number, you can write like this: minus the absolute value of phi 22 times sine of omega 2t. That's why you see this has a minus sign, and so D22 has a minus sign, D21 has a plus sign. So when D21 is positive, D22 is negative, right? So that's why you see that the two sine curves are opposite. But in terms of the phase angle, this is active learning credit here. How do you so let me give a hint here. How do you write sine of omega 2t plus the phase angle? Usually phase angle is also denoted by phi, you know, but so now let's call it alpha. Okay. What would be the value of alpha? Excellent.
Would it be 180?
Yes. If alpha is pi or 180, then you get the minus. Very good. What's your name?
Tony?
Tony. Team 7?
Yes, sir.
Let's see. So that's why I said when the vibration is out of phase, then Tony team 7, then the phase angle is 180 degrees. Okay. Yes. Okay. Very good. So we make a lot of progress now. Right here, so I already finished with the animation. Now the mass orthogonality of the normalized eigenvectors. Okay, remember, why do you normalize? What's the motivation to normalize in the regular standard eigenvalue problem, where the mass matrix was an identity matrix. What does it mean, normalization? You know, when you take a unit vector, dot product with a unit vector, what's the result? The unit vector dot product with a unit vector. What would be the result?
It's just one. Yeah, is it just one?
Yeah, Tony again.
Tony?
Kevin too. One, yeah. Normalizing means that you make the length equal to one. Make the length becoming a unit equal to one, yeah, unit vector. So in the case where the mass matrix is not an identity matrix, this is very similar, and it's expressed with the initial notation, where delta ij is called the Kronecker delta. Okay, what it means is as follows. The Kronecker delta is defined delta ij equal to 1 if I equal to j, and equal to 0 if I different from j. What it means is as follows. Okay, very simple. Phi 1 transpose m phi 1. Maybe I should write in my notes so you get it. Equal to 1. Okay, maybe I should write in my notes so you have something left. And I have something to review for you as well. So what it says is the following. Phi 1. Oh, now we need the bar, okay, because we already normalized. Times the mass matrix times phi 1 bar, that's equal to 1. Because in this case, I equal to j equal to 1. So therefore delta 1 1 is equal to 1, right? Because delta, the Kronecker delta, was defined as equal to 1 when the two indices are the same. Okay? That's what you see in this definition here. Right? When the two indices are the same, then the value of the Kronecker delta is 1. When the two indices are different, then the value is 0. That's all that is. Very, very simple. But it allows you to write in a compact form. Okay, so now let's give another example. And this is opportunity for active learning credit here. Okay, what is, if you replace both indices by 2, what's the result? Oh, quick, Brennan. 1, yes. And now I'll call you next, okay? So you will come up next. So if I replace only the second index, with 2, yes. 0. Yeah, so Brennan and what is your name? Brennan, what team? Team 1. Oh, so team 1. Okay. Team 1, Brennan, team 3. Taylor, first time very good. Keep doing this. And Brennan, team 3. Okay, I'll pick you next direction. See if I can. This is what time do we have? Yeah, let's see have time. So direct you can contribute here. This is 0. And now if I do this, and I swap these two indices, so P2. I need to have the transpose here. Okay, here transpose. Okay, and Phi1. So what's the 0? Yes, that's it. Very simple. Because the two indices are different. So you see, instead of writing 4 equations like this, with the Kronecker delta, you only need to write 1 compact equation. Okay. So the rank is teammate. Let's see. Yes. Very good. Okay, so let's see what I have more to say here. Yeah, so before we finish, this is the this is the result of the normalization with respect to the mass matrix. So you introduce a new matrix, big phi bar. Remember before, without the overbar, that's the unnormalized eigenvector. So now, with the overbar, that means the normalized eigenvectors. These are the two eigenvectors. Okay? And these two normalized eigenvectors, phi1 bar and phi2 bar, satisfy that mass orthogonality relation. It's very important. Phi1 transpose M phi j, phi1 bar transpose M phi j bar equal to delta I j. Okay, very good. So I think please write the lecture summary and any critical thinking questions that you may have. Yes, the team signature sheet is down here.
What did you get this test? Hey man, you send me pictures.
Yeah, I just left it. I left it as a drink.
I fell asleep. No, you can bring it on. Oh, but that's too late. I emailed you. I'll text you tonight. No, I forget. Text me. I'll send you an email.
Oh, the video camera. Go for it. Why is there one right here? I don't know.
Yeah, let me turn off.